Hello everyone, so we're on the Cranfield University campus in a county called Bedfordshire in the UK, and we're going to be talking to Professor Naresh and Carla, who are our colleagues on the EWA-BELT Project. So we're wandering around the campus. We're going to go and find them in a minute, but they'll be telling you a little bit more about the post-harvest technology work that we're doing on the EWA-BELT Project and how that's shaping up. So good. So yes, we'll lead you through them now directly. Okay, John, so just tell us where we are.
Okay, we are Cranfield University campus, and we are just by one of the big buildings here, the Vincent building, where Prof Naresh and Dr. Kara are based. We have the lab here, the mycology unit where they work, and we're following up on some of the activities they are doing. There's research they are setting up on the EP3, that is on post-harvest technologies.
Brilliant, thank you. Let's go and see them now.
Okay.
And they've got 3 shelves.
Right. Naresh, can you start again? Explaining how that works?
Okay, we have some aluminium cans which are available everywhere, and they've been painted black. So we have a series of aluminium cans here, and you can use the light of the sun or lights to get the heat moving through the cans and passively up through this structure, and then you have trays on which you can put your peanuts. We've got 30 kilos of peanuts here which we're going to test, and we can use maize, cowpeas maybe, or other commodities for looking at how efficiently you can dry it. And you can build this from local materials. This was designed initially for peanuts in Ethiopia, but we think it can be applied generally in sub-Saharan Africa, because it's all got quite cheap local materials would be available.
So it's very low-tech.
Low-tech system. We're going to test it with peanuts.
Ah.
I bought 30 kilos of peanuts in the shell from a wholesaler near where I live, and we're going to test it with that. So we're going to use, you can use different moisture contents of commodity.
Yeah.
Put it in there and see how efficient you can dry it, and you're going to measure the temperature change.
Yes, and also
and the movement of the airflow through the system, depending on the amount of heat you apply here.
Yes.
So the idea is to use the sun's heat.
Yes.
Yeah.
Brilliant. And you made that in Angel's garage, is it?
Yes.
We've made it in Angel's garage.
Yes.
So it really is low-tech.
And you've got a design.
Yes, we found the design online, actually on YouTube. We took inspiration from that, and then we optimized it a bit, because on that one, they did include some valves here, some holes.
Some vents.
Yes, in order to let the flow coming from here, where we have the cans open, so flow inside and also go outside. Otherwise,
you need an exit point for the moist air after it's been through the commodity.
Yeah.
So it creates a flow, doesn't it?
So you have
Airflow.
a perforated tray.
Yeah, exactly.
3-4 trays there, so the air can go through the trays and dry the.
Yeah.
So they'll be looking at the drying efficiency. So they'll start with, say, intermediate moisture peanuts in the trays and see how long it takes to dry and measure all the parameters.
So does it stand outside in the open, or?
Yeah, that's the whole idea.
So it would need to be
outside.
waterproof, I guess, or?
I mean,
yeah. The idea is to optimize it. It needs to be outside, to include some waterproof also materials.
Yeah.
At the moment, because
it's a test system.
Yeah, it's a test system, and then because of the light in UK, that is not potentially the same as Ethiopia. So we thought to buy this infrared lamp that will warm up instead of sun.
Okay, so you'll test it inside.
We're going to simulate
simulate
LED lights to get the right temperature that they want. and they're able to measure the airflow and the temperature inside, depending on how much LED light they give.
And then you'll really put some peanuts in it and test
We
it.
have them
We're
already.
ready.
We're just waiting for
So look at the peanuts.
Yeah, we've got 30 kilos ready.
Whoa.
Yeah. I bought it myself.
And then will you test them by eating them, or
No, these are not for eating.
give them to the students?
These are feed grade or bird feed. It's more for,
Ah, those sorts, yes.
you cannot buy peanuts in the shell very easily for human use in a 10 kilos at a time.
Yeah.
Buy them in a small bag, but we needed
30 kilos.
30, 50 kilos.
Yeah.
You can't buy
So
it.
it's
We
only
look
for birds.
everywhere.
It's only for birds.
Yeah.
We'll test it on the birds.
And some of them say they are aflatoxin free.
Ah.
In Amazon it says.
Yes, true.
But I don't know where that comes from. I don't believe
We'll
it.
see.
Yes.
If it comes from China, it'll definitely have some aflatoxin.
Yeah. So I guess you have a control somewhere then, will you? Will you have another set of peanuts somewhere else just to see what happens?
No, because we already know that the big problem is, by starting with different initial moisture contents,
Yeah.
you can go from safe conditions to intermediate to unsafe.
Okay, so it's the conditions, yeah.
Your control is actually dry peanuts.
Yeah. Okay, so it's the conditions you're monitoring then, isn't
You
it?
start with, if you harvest peanuts like in Ethiopia, they store them quite wet initially in a pile.
Yeah.
And the problem then is they allow it aflatoxin, the mold to grow, and you get a high amount of aflatoxin there naturally. So by the time they start using, they can't use it to make these, what do you call them?
Ready to use therapeutic food like
For-
plum
for-
peanuts.
Plum peanut and some for therapeutic foods. They can't use local peanuts. They have to import from India and so on. And it's quite expensive because the aflatoxin level is too high. So the idea is to provide on a local scale a method for more efficiently, when you've harvested the peanuts, to dry them in this type of system than leave them in a pile. So they can use more local peanuts for producing these energy bars. Yeah.
So this technology is actually being done for Ethiopia situation. So I'm looking at in terms of temperature, because I'm looking at our scaling it to the broader usage. So I'm looking at how will it fit within the environmental conditions. How would this help deal with that?
How much would it cost to make one of these? Have you calculated the approximate cost as Angel or?
Yes, but in our case, so considering that we should use some reusable materials, well, we bought them. So the idea would be to start with
Available
wooden.
It's a laminate material.
Yeah.
You need some nails and screws. The cans are
Yeah,
available.
the cans, yes, but
Need some perspex.
yeah, overall it should be made. The ideal would be to create it with ready available or materials. So because
It doesn't look too complex to me.
No, this plywood.
No.
Plywood is
exactly,
pretty
that's
easy.
plywood.
Yeah,
It's just
quite
plywood,
common.
some wooden piece.
The cans are available.
Yeah, the cans are available.
And they can easily spray paint the cans black.
Yeah.
That's easy.
Yeah.
So they are open.
Yes.
It's like it's really a passive kind of solar dryer
Okay.
by using cheap materials.
Okay.
So we use the sun, heat of the sun, and move it through.
So the what do you call it?
This is the heat capture.
The heat capture.
Yeah.
What you introduce, the heat you introduce, I hope it's similar to the situation in Ethiopia. I don't know whether you're looking at that. The temperature.
Well, they're going to check.
Okay.
Yeah, we still need to check,
Yeah,
and we're gonna start.
Okay.
But you're going to use the infrared lamps, is it?
Yeah,
To heat?
exactly.
Yeah,
At the
and
moment, that's
then-
what we can do because we try to
To
find
simulate.
a place outside, like in a glass house, but it was not good, the environment around. So we're gonna see first if it's working, and then potentially if it works, maybe try to put it in a more similar condition to what is outside condition, if possible, but all the climatic environment here is different, so we need to adapt it somehow.
Next spring, summer, we could try it outside. They got some
new.
and the idea is to have these so that then the heat
Comes
can
to
go 1, 2, 3, 4, maybe 5 or 6 trays.
Yeah. So it comes out of those holes, the heat.
Yeah, the heat comes out there and it should go up.
Through the
when
peanuts.
This is closed, goes through. So they're going to put layers of peanuts there. Different, specific starting moisture content, and see how long it takes to dry. 2.7 water activity, which is like about 7.5% moisture content, which is then safe for storage.
So it carries the humidity out of the peanuts, doesn't
Yeah,
it?
it comes out here. The vent is here, so the moist air should come out there.
Brilliant.
Yeah. This would be great in a village, for a farmer to have one, because you could use it for different commodities. If you have maize or cowpeas, peanuts.
So looking at
How?
maybe you could dry half a bag at a time. Because what is the capacity? Like this one, what's the capacity?
That's a good question.
Can it take?
We have to check.
Yeah,
Okay, you need to
we
check
can
that.
reply as soon as we can try.
Yeah, sure.
Yeah.
So like
I think if you have 1, 2, 3, 4, 5 trays.
But even more, because
One,
we,
two,
yeah.
three,
the idea was to do other
four,
trays.
five, six,
So.
seven,
But you may want to move the trays around, because
Ten.
what
It's picking
happens
10. Yeah.
no, but what normally can happen is the moisture in these layers dry, and it reabsorbs in the top layers.
Yeah, that's
So you then have to move those layers down. You don't want to over dry the bottom
okay.
and under dry
Dry
the
the
top.
top, yeah,
so
So it
you
needs
maybe
some
take the
level
top
of,
3, and then you after so much, say 1 hour or whatever, you move the top 3 there,
yeah.
and the bottom 3 up and down.
Down, yeah.
So how long would you have to leave the peanuts in there to dry?
Well, say you start with 50% moisture or 20%, you want to go down to about 7.5%, which is equivalent to 0.7 water activity, so no mold will grow. And then you use that as your measure. So we've got a water availability machine in the lab. We can put some peanuts in there. And we've also got a portable one actually we can use,
Okay, yeah.
which we've used for Brazil nuts. So we can actually take it and just measure it.
Okay.
We can take samples from different layers
Yeah, and
and just
monitor,
check.
yeah.
Monitor the rate
Moisture,
of...
Yeah. But it's. Do you think it's a matter of hours or days or weeks, or how would it?
We would hope hours.
Yeah.
Ah, really? Okay.
I would hope half a day,
Yeah.
depending on
Okay.
the moisture
Yeah,
content.
so it's very efficient. It means it can do a lot within a short time. And that's very
Yeah,
good.
we
Yeah.
will tell. We will tell you as soon as we are able to test, because we really want to know.
Yeah, it's really be interesting.
Yeah. So hopefully.
It could be a very economic way of, capacitive drying
Yeah.
at a reasonable cost.
Costs, yeah.
Yeah.
Yeah. So we just need to test it.
Okay.
Brilliant.
And it is
So-
simple, it's nothing fancy.
Yeah.
Yes.
You could make it more sophisticated with sliding, good
But
stuff.
if they can do drying in half a day, I mean, there's a lot of. Then you could use it for a lot of peanuts, isn't it?
Yeah.
I mean, it's not just.
Well, say you
could do hundreds of kilos.
In, it depends if it's in a shell or unshelled.
Yeah.
If it's shell peanuts, they usually store them in 20-kilo bags. Those Hessian bags and so on. So you'd want to be able to do 20 kilos.
Yeah.
If you can do 20 kilos in a day, that would be good.
Yeah.
You could do 10 kilos and 10 kilos,
Yeah.
then that's done. And if you sun dry in some others, you can then put them in here to finish them off.
Yes.
That's the idea. Because they also have problems, I know in West Africa with cowpea, there's a pest. which damages cowpeas,
Yeah.
and they use a lot
The
of
weevils,
pesticides,
yeah.
weevils, and they have a problem exporting
Okay.
cowpea
It's actually
because of the
compromises
residues
Yeah, yeah.
of the pesticide.
Yeah, the pesticide they use for
So
storage.
if you can efficiently dry it first,
Yeah.
you may
reduce
lose
the need for that.
Yeah. as well. Yeah, that's good.
Ah.
Thank you very much, Carla. Excellent.
It's a pleasure.
Yeah, thank
Can't
you.
wait for it.
Thank you very much. Do you want to just say where we are? So we're standing in,
Vincent Building,
yeah,
third floor, and Cranfield University. Yeah.
In our environmental laboratories.
Yes.
yeah. Okay, because there's huge. Actually, we're in a huge lab, aren't we? This is just one of the rooms,
Yeah.
but there are lots and lots of rooms, and then there's a great big room outside with all sorts of equipment. So that's all soils and water and mycology,
Here
is
it's
it?
more water and molecular biology and so on. And we are mycology. We are downstairs on the second floor in the other lab where we were. We've got 2 or 3 benches, and all our group is based around there. But we use molecular equipment up here, and this is a kind of a workshop room.
Yeah, they gently gave us this room to put our peanuts because we didn't know where to put it to test it. So.
Right.
Yeah.
Okay, that's good.
Excellent.
Yeah.
Well, thank you.
You're welcome.
Thank you very
need
much.
a Cranfield University logo.
Logo.
Before they steal the idea. You never know.
Yeah, it's true.
Yeah.
Get the logo on
Use
there.
a little logo on here
Yeah.
and on the other side. Even if it's a piece of paper, just stick it on here for now.
Yes. We thought about doing
Yeah.
it.
No, you need that C Cranfield.
Cranfield, yeah.
If you or agri-food, environment and agri-food, whatever, just have the logo there. And of course, the Applied Mycology Group logo. Why don't we just use a Applied Mycology Group logo?
Yeah.
Even better.
Yes. Leave out Cranfield.
No,
Yes.
it's got Cranfield University.
On it.
Ah, does it?
Applied
It's got
Mycology
Cranfield.
Group, deciphering, what's it?
Something.
Fungal complexity.
Ah, okay. Yeah.
We have our own logo.
Very good. Yeah, that sounds good.
fine.
Stick one on.
Yeah, that's fine.
Yeah.
I think,
Oh, you've done a great job
What do you
there,
think?
John.
Okay.
it was,
Okay.
yeah, yeah, good.
Okay. Thank you.
Yeah.
So this could apply to not just the Nutri-Nuts project, but also to EWA-BELT
Yeah, sure.
as well.
Okay.
Yeah. To EWA-BELT as well. So,
Yeah, exactly. No,
Yeah.
brilliant.
great.
So say hello, everyone, or say goodbye.
Bye.
Bye.
Great.
Mobilized only. So we needed the full. So this is the kind of size of the sheet. I think I've got a slightly bigger sheet now. Get into this. Okay, let me take a sheet out. Okay, here's a small sheet. So what we've done is actually, so this is the sheet here.
Okay. That was very thin.
It's dual release. So the idea is it's immobilized, the sodium metabisulfate is immobilized on this surface. So when you make a bag like this, you can put your granule there, and in air it slowly releases the sulfur dioxide, and it acts as a preservative. So depending on your concentration of sodium metabisulfate you immobilize on that surface, you can compare the effect. You can put different moisture contents of maize, peanuts, cowpeas, whatever in here, and check whether it controls foliage and mycotoxin contaminants in there.
Okay.
And the biggest size, I'm afraid they make is about this size. Maybe twice that size, but that's not big enough for a 20 kilogram bag. So we can make a bag for about 5 kilos. We could put, the idea was we could put 2 of those together, vacuum seal it, and send like 25, 50 bags to West Africa or East Africa for them to test. That's possible. But it will only be a bag about, yeah, this size, with 2 sheets together, yeah, with an open side and then seal it at the top here. And these are being used with one concentration for fresh horticultural produce like grapes to control botrytis, kiwi fruit, a lot of export fresh commodities. They have this inside the boxes to release the sulfur dioxide to control pathogens. So we are the first to look at it in terms of grains, cereals, maybe beans and so on to see whether we could use that for controlling spoilage and mycotoxin contamination. So we originally had 40, 60 and 70% immobilization. Now we've got to 70%. And we know that it releases the SO2 over the first 48, 72 hours predominant, and then slowly releases a bit more over time. Yeah. At 4 degrees it doesn't release anything. And if you vacuum seal it, then it should be fine for up to a year.
Oh,
so
really?
You can keep
Yeah.
the sheets for longer.
So you put that inside a jute bag, do you?
The idea was that we could have these layers inside the jute bag.
Yeah.
So you could make a bag, in a bag,
Standard jute.
a stitch in a bag
Yeah.
with these layers and put it inside a jute bag. Or even a polythene bag, whatever.
And then that would,
my idea.
yeah. And it would protect for
It will protect
1 year or so, or
well, the
6
idea
months.
is it releases it maybe 75% in the first few days.
Yeah.
So even slightly moist to control molding, and then it still releases a small amount residually over time.
Yeah. Yeah. Okay.
Yeah. So we've got some data on maize.
And the idea is to do a lab experiment soon, isn't
We've
it?
done some lab experiments
you've
with
done.
maize of different moisture content already. And we're going to do some experiments with peanuts, shell peanuts, and hopefully with cowpeas as well.
Okay.
And sorghum. Oh, what happened to my sorghum? Where's my sorghum? In the 40-degree room?
Yes.
Okay, fine. And sorghum.
And sorghum, right.
Yes. I had to buy 4 kilograms on Amazon because my colleagues in IITA in Nigeria said it's too complicated to send the sorghum. You need all kinds of permits.
Ah.
So I just bought 4 kilograms on Amazon.
Just like that. Well done.
Okay.
Brilliant.